All right, guys, let's think about this other really important parameter, steady state kinetic parameter, in thinking about enzymes. We talked about kcat, both in terms of the simple mechanism and a more general interpretation. We've talked about km the same way. It turns out the ratio of kcat to km is a really important parameter for understanding key aspects of enzymes, right? So to get into explaining this, consider what happens to the expression for a steady state enzyme, the initial rate equation, at low substrate concentration. So let me just write this out. So if we think about the initial rate again, remember that's equal to kcat times the concentration of total enzyme we have times the concentration of substrate divided by km plus the concentration of substrate, right? So the question is to think about in the limit where the concentration of substrate is much, much less than the km, what happens to that equation, right? Well, for one thing, what's going to happen is the concentration of total enzyme is going to approximately be equal to free enzyme, right? As you get much, 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 much less substrate, most of the enzyme ends up being unbound to substrate. So most of the enzyme is so-called, would be free enzyme. At the same time, under that set of circumstances, so that's one thing, under that set of circumstances, what happens to that ratio, right? If that sum in the denominator, if concentration of S is much, much less than Km, S becomes kind of insignificant in that sum, right? So we can kind of cancel that out under this set of circumstances, right? So in that limit, the initial rate then is equal to kcat divided by Km times the concentration of free enzyme. Remember, that's our other element here, right? That the concentration, total enzyme concentration is now approximated by the free enzyme concentration times the concentration of the substrate. Now, if you look at that expression for a second, you see a couple of really interesting things about it, or you should, right? What does that expression look like? If you think about this reaction, enzyme plus substrate goes to enzyme substrate, and now it goes to enzyme plus product, right? Or let's say we can make this go away for a second. If I just sort of ignore that. But if I wrote this out a different way, enzyme plus substrate, and it goes to enzyme plus product. What this looks like, excuse me, in this case, right? Maybe I'll just write this out a different way. What if we had enzyme plus enzyme plus substrate? Do this a different way, right? Goes to ES, right? And I had a rate constant here. If we wanted to know how fast we were making ES, right, that would just be K times concentration of E times concentration of S. And we would know that was a bimolecular rate constant, right? And then, of course, this turns on into E plus P, right? So if you look at that expression and you look at that expression, does that look familiar? Or does it look similar? Yeah, it's exactly the same form. So basically, what kcat over km represents, right, is a second order, or an apparent second order, excuse me, binding constant for the rate at which the reaction generates product relative to or governed by the rate that the free enzyme binds to the substrate, right? or said another way, kcat over km tells you essentially how effectively the enzyme interacts with the substrate to make product. And it is, if you look at the units of this expression, it absolutely is a second order rate constant, right? Because what's kcat's in units of second to the minus one, right? And km, right, is in units of molar, which means the units of kcat over km is second to the minus one, molar to the minus one, same as a bimolecular rate constant, right? And so the form of this equation, like a constant times E times S, is, as I said, a apparent second order rate constant for the interaction between enzyme and substrate, but related to the rate at which product is produced, right? So the kcat over km is such a useful and important parameter because this parameter tells you something about both the specificity and the efficiency of an enzyme, right? So as an example, way to think about this, the higher kcat over km, right, the larger this number, right? If you think about it as a bimolecular rate constant, the larger that number gets, the faster the binding reaction happens. But in this case, we're relating the rate of the initial rate of an enzymatic reaction, right, to the essentially the rate at which the free enzyme interacts with the substrate, right? So the larger that number gets, the faster the reaction is going to go, right? Or another way to think about it is the larger kcat over km gets, the more likely the Michaelis complex goes to enzyme plus product, right? As kcat over km goes up, this reaction is more likely to go this way rather than go the other way, which would be enzyme plus substrate decaying back to E and S, right? So the higher the kcat over km, the higher the probability that the reaction is going to turn into product rather than go in the opposite direction, right? So as an example of this, right, we've got a parameter that is relating the rate of a steady state enzyme reaction to the interaction or the rate of interaction between the enzyme and the substrate, right? So another way to think about this would be if you consider what would make an enzyme maximally efficient. Right? When would an enzyme be as efficient as it could possibly be? It would be one that would carry out a reaction every time it correctly engaged the substrate in its active site, right? So each and every time an enzyme found substrate, it would always make product, right? Right? Okay. So essentially, it would never fail. It would almost never, miss or let go, right? It would basically be so-called catalytically perfect. All right. Well, that would be related then to how frequently the enzyme substrate could bump into each other in solution, right? So that would be related to the diffusional encounter probabilities of two things banging away on each other in free solution. And at 25 degrees Celsius, the rate constant for bimolecular banging into each other of two things in aqueous solution is in the range of 10 to the 8th to 10 to the 9th per molar per second, right? And for some enzymes, like, oops, uh-oh, I seem to have lost my screen sharing. There we go. All right. So at 25 degrees, the bimolecular rate constant, as I said, for the rate at which two things in aqueous solution can whack into each other is in the range of 10 to the 8th to 10 to the 9th per molar per second. And for certain enzymes, like fumarase, we haven't encountered these enzymes yet, carbonic anhydrase, which we have, and triose phosphate isomerase, these enzymes have kcat over km values of approximately 10 to the 8th per molar per second, which means these enzymes have achieved what could be called catalytic perfection. Every time they encounter a substrate molecule in solution, every time they bang into one and engage it and it's in the active site, they produce product, right? So this is why this parameter, kcat over km, is so important in thinking about enzymes, because of the way in which it relates the observed steady state rate of the reaction to the concentration of free enzyme, right? And the efficiency with which that enzyme can then carry out catalysis, right? Okay, so there's a problem here with how I've gone through this. Right? And the problem is that to sort of set this up for you guys, what I've done here is take a shortcut. I've sort of done this sort of way you often see this kcat over km expressed to people by thinking about the steady state, simple steady state initial rate equation in the limit of very low substrate concentration. All right, so big flashing red sign. This leads some people to think that kcat over km only applies when the concentration of substrate is much lower than the km. That is wrong. Underlined, big red sign, flashing, flashing, flashing light. kcat over km applies at all substrate concentrations. It's a fundamental, apparent second order bimolecular rate constant that relates the rate of the reaction to the concentration of free enzyme at all substrate concentrations, right? It's this apparent bimolecular rate constant that it cannot be any greater than any true second order rate constant on the forward reaction pathway. And it sort of sets a lower limit on how fast enzyme and substrate can bang into each other, right? But that applies at all concentrations of substrate, not just under the special sort of circumstances I limited here to get to this expression. This is just an easy way to demonstrate the idea to you guys, right? But the really important point is it doesn't just apply under this set of conditions. And this is where we come back to that definition I gave you guys before for Km, right? As this apparent dissociation constant between the free enzyme, substrate, and all possible bound forms of the enzyme, right? Now, I'm not going to go through it. If somebody's interested, we can go through it in class at some point, or I can show you guys the derivation. But using that definition for Km, right, you can derive exactly the same expression here for kcat over km, right, without this assumption of being at silly low substrate concentration. In other words, by using this definition for Km and going through a fairly simple derivation, it is possible to show that this expression for kcat over Km, or the relationship between the reaction rate and free enzyme, applies at all substrate concentrations, not just at these super low concentrations. So again, I know I'm going around in circles here on this, but I want you guys not to mess this up. Kcat over Km is a critical kinetic rate constant for thinking about enzymes at all substrate concentrations, right? In relating the ability of the free enzyme to bind the substrate and convert it into product, right? Okay, I've beaten that dead horse enough. So that's sort of on the sort of efficiency side of things, why kcat over Km is so important, right? You can see that as that number gets bigger, the enzyme gets more catalytically efficient, right? It requires fewer binding events to create product, and that number gets lower. The enzyme spends more of its time bouncing around and letting go of stuff before it actually makes a product, right? Okay, but there's another reason why kcat over Km is so important, and this has to do with this idea of specificity. Sometimes you have enzymes that can interact with two different substrates that are similar to each other, right? For example, we could have an enzyme that could work on, say, a substrate molecule B, right? Or maybe you could work on a substrate molecule, we'll just call it A, right? So we could have then the EB Michaelis complex or the EA Michaelis complex. And then we'd have a rate constant here, K sub B, the equivalent of the kcat for substrate B. And we'd have a K sub A, which would be the kcat for K sub A, right? And so the question is, if you had A and B present at the same time, which one wins? Which pathway, if they're both here at the same time, which pathway does, or which path dominates the production of, or which pathway dominates what the enzyme does, right? Which product of which substrate is what's mainly produced under some given set of circumstances. And this is where kcat over Km comes in really, really, really useful, right? So remember, in both cases, what's going to determine the rate of conversion is going to be how well each substrate, A or B, bind to what? The free enzyme, right? And remember what we just talked about in terms of why kcat over Km is so important. It relates the rate of the reaction to how well the substrate interacts with, binds with, and is worked on by the free enzyme, right? So that's great, because what that means is we can write out a couple of simple expressions. We can say the rate at which concentration of A changes with respect to time, right? We can just call that V sub A, versus B with respect to time. That's just going to be VB, right? And we know, based upon our little discussion, that we can relate that to the kcat over Km for substrate A times the free enzyme times whatever concentration of A we have in this particular competition experiment, for example. We can do the same thing here for B. We can say kcat over Km for substrate B times the concentration of free enzyme times the concentration of B. Now, the question I posed was, well, which one wins, right? And you can answer that by saying which reaction under a given set of circumstances or a given amount of A and B is going to go faster, for example. Okay, well, that's pretty easy then, because all we got to do is take the ratio. We can just say the rate, again, we're under steady state conditions here, the initial rate at which A or B dominates is just going to be equal to the ratio of those two expressions, which is just going to be equal to the kcat over km for substrate A divided by the kcat over km for substrate B, right, times the amount of A I've got versus the amount of B I've got, right? The E's cancel out and you take the ratio, right? So by knowing the kcat over km for an enzyme with respect to some given substrate, you can compare how well it works on that substrate versus another substrate at a given set of concentrations to determine how well it's going to make the product from which of those two substrates. So it tells you a lot about the specificity of an enzyme for a given substrate molecule. And this is one of the other reasons why kcat over km, in addition to that discussion we just had about efficiency, catalytic efficiency, why this parameter is so important in steady state enzymology.